So hello everyone, good evening to you all. I'm Ranganath, undergraduate student of Sabaragamu University of Sri Lanka. So today we have one of the fabulous lecture series with us. So let's see what is going to get aligned in the rest of the lecture. So first, I would like to proceed by starting what SEDS Sri Lanka and 𝐍 is. SEDS Sri Lanka is a part of an international organization aimed at promoting space exploration and development through educational and engineering projects. SEDS Sri Lanka has received many accomplishments over the years. When talking about 𝐍, it is one of the chapters that is unfolding under the entity of Sabaragamu University of Sri Lanka. The 𝐍 intend to organize this annual webinar series as a help to the NASA Space Apps Challenge 2021. So what is this NASA Space Apps Challenge? This is the very first international hackathon event in Sri Lanka in collaboration with the NASA. And this NASA Space Apps Challenge 2021 is the second episode of that. Starting from today, we are conducting some of the webinar series that will be very useful for the participants who are willing to take their participation in NASA Space Apps Challenge 2021. So I'm pretty sure that this webinar series will be so productive and informative as well. Today, we are unfolding the first episode of the series under the theme of satellite image processing. So, for the participants, in case if you meet any questions or comments regarding our session, we are using a question and answering session at the end of the lecture. You can use either the chat box or you can raise your hand only once the Q&A session is open for you. So I'm repeating, in case if you meet any questions or comments regarding the session, we are using a question and answering session at the end of the lecture. So you can use either the chat box or raise your hand only once the Q&A session is opened. So today, to conduct a very valuable lecture under this topic, we have a great personality with us. It is none other than Dr. Duminda Welikanna. As a person who is really busy, thank you so much, sir, for giving us your valuable time. So I cordially invite Dr. Duminda Welikanna. Sir, the floor is all yours.
Thank you, thank you for the invitation from SEDS, and it's a pleasure to be here. When this NASA Space Apps is going to happen soon, so everybody is interested in space images and space science. So I did a lecture last year also in parallel to these NASA Space Apps for SEDS Sri Lanka. This is specifically for satellite image processing. So without going into much, I will just start my lecture. I hope everybody can see my presentation. Okay. So satellite image processing, what is this? Where in an age where satellite images are very frequently used, everybody is interested in this image processing. And you know that a lot of sensors, in different type of sensors, are coming up by NASA, ESA, and JAXA. One very important mission is going to launch in 2023, that is the space-based LIDAR sensors from JAXA. And most fortunately, one of the students or one of the graduates from our faculty might get the chance to join this very important mission. So that is some inside information for you. So I'll start about this processing of satellite images. What you see is satellite image from synthetic aperture radar over the ancient city of Kandy. As you can see, this is the Victoria Dam and the Kandy, where it is located near the Mahavali River basin. This is a backscatter image from decibels, converted into decibels. So this is kind of a satellite image that we get to process. You can see a lot of information in this, but all the information are not relevant for us. We are interested in particular information. As you can see, the yellow color areas are the urban areas quite close to Kandy. Now, going into the details, remote sensing, mainly when I talk about remote sensing, I talk about remote sensing in three aspects, in three basic subsections. One, we can talk about remote sensing on the purpose of imaging or non-imaging. And also number two, on the top right corner, we can talk about remote sensing depending on the sensor, whether it is active or passive. And then in the bottom, bottom right corner, you can see we can talk about remote sensing depending on the wavelength or the electromagnetic radiation. As you can see, increasing energy into the left direction and increasing wavelength into the right direction. So I'm talking about imaging sensors. So we have imaging sensors in optical region, that is visible and infrared region. When you say infrared region is very large. As you can see in this electromagnetic spectrum, infrared region is a very large region. So it has infrared, near infrared, short wave infrared, and also thermal infrared. So all these regions are being imaged by sensors carrying on top of satellites. So imaging sensors can be subdivided into optical, thermal, or radar images, and non-imaging sensors can be spectroradiometers, and laser range finders, altimeters. Most of these spectrometers, radiometers, and non-imaging sensors work in long wavelengths. That means away from microwave to radio wave. But in the imaging sensors, they are more concentrated over the visible, infrared region as well as microwave region. So thermal sensors detect the emissivity, while the optical sensors detect the reflected energy, while of course the radar images detect the scattering properties from objects. So in order to process a satellite image, we have to understand what this image is talking to us about. It's a language, and we should understand how to read it. So passive and active sensors, of course, you know, passive sensors depend on sun's radiation, and active sensors, they depend on their own energy. So radar sensors are active, passive sensors are thermal, and optical sensors are passive sensors. And in a summary, if I say remote sensing, my definition of dividing remote sensing based on the purpose is mainly where these sensors work on the electromagnetic spectrum or the wavelength. So each sensor is dedicated to a particular wavelength region. Now, we have to understand the imaging geometry a little bit if you really want to understand a satellite image. Mind you, I have to say that I didn't put the content, I'm sorry about that, but my talk is about a little bit of introduction to remote sensing and sensors and the images, and then I'll be talking about key areas of satellite image processing. One is classification, two is change detection. In my today's lecture talk, I will be talking about these. Three is image fusion, and fourth one is actually segmentation. So these four areas I will be talking about. And also, I will not be talking about the in detail theoretical aspects, but after the end of this lecture, you will understand where you have to search, or you have to read, or which area you are really working on when you're working on a satellite image on a specific purpose. For some people, they are working on disaster. Some people, they are working on forestry. Some people, they are working on engineering. Some people, they are working on atmosphere. So each area, when it comes to these different diverse areas, you have to understand as a operator, you have to understand what am I doing to this satellite image and which area should I work on the scope of processing. So this particular slide talks about imaging geometry of two specific satellite sensors. One is active, the other one is passive. What you see is this optical image. You can see optical images have onboard sensors and they look directly down upon the nadir. Nadir is directly down upon the sensor. So their image is actually imaged on this red line, along this red line. As you can see, objects in the nadir that is directly beneath the sensor and off nadir will be imaged. So once you get a satellite image from optical images, thermal images, that means active sensors, it is much more easy for you to read or interpret the image because it is like you're taking a picture from your camera. You won't take pictures from your camera obliquely, that means sideways. You always try to take a picture using your camera directly orthogonal. So it's an orthogonal projection. So optical images are easy for your eye and much more easy for you to interpret. But when it comes to microwave sensors like synthetic aperture radar sensors, they don't image as such. Their geometry is different. As you can see, sensor is somewhere away. They don't see the nadir area. That means directly beneath the sensor, they cannot see. They see an oblique view. That means a sideways view. And their image is imaged on a slant plane, as you can see this green line. So these images are much more difficult to interpret, need advanced image processing techniques to put down to the level that you can extract features or extract information from. This geometry is very important, and this is one reason why the psi antennas cannot see beneath it, because there is a parameter called incidence angle. And when the incidence angle is 0, incident angle is 90 degrees, that means from the parallel to the perpendicular, there is no resolution for the image. I will talk about what resolution in few minutes. So basically, because of this incident angle parameter, that is the angle that is antenna looking sideways, when it becomes 0, there is no possibility of getting an image. So that's why mainly it is side looking. But there are reasons, a few more reasons why it is looking sideways. It's working on longer wavelengths, not like the optical sensors. And due to few reasons, the psi antenna cannot see directly down. So I won't tell you because all you guys are from Sri Lanka. You know that there was a ship, actually Express Pearl, which was on a disaster. And I have seen an image from Sky News that taking a satellite image, it says it was a satellite image directly looking down upon the ship. So the first thing that you should know as a satellite scientist, that this image was taken by an optical sensor or maybe airborne drone, not by a SAR sensor. So in that case, most probably these images should have cloud effects. And when it comes to optical image, one very difficult reason why we can't get images of Sri Lanka is because Sri Lanka is quite close to the equator and it is affected by monsoons and it is always cloud cover. So the applications of optical sensors are very limited in Sri Lanka, while the application of SAR can have very detailed and very large scope. But the application of SAR sensors in Sri Lanka is very, very minimal. Now, I'm going to talk about elements that you have to understand in basic for satellite image processing. So now just look at this these properties that can occur when a sensor passes on top of a particular area on the Earth. So sensor sends, say this is an active sensor. That means it sends energy and it's try to record whatever coming back at the sensor. So if it hits something like water, you can see its surface is like a mirror. So most of the energy is scattered away, and because of that, there can be no energy coming back to the satellite. But when it hits a vegetated area like a forest, you can see the energy hits, and because of the canopy and its heterogeneity, the scattering can happen, or the energy can be disturbed. Scattering is something like that. I'm not going to talk into detail about these technical terms, but you can just mention them down and you can read a little bit more to get an idea. This scattering process is like volume scattering, and part of the energy is coming back, and it is very, very minimal. And because of that, this energy coming back can be median. And this doesn't have energy coming back, so the object is going to be like dark, because there is no energy coming back and you can't see. It's like the sensor can't see anything. But in this medium case, you can see that there is a little amount of energy coming back, so it is like medium. And when it comes to urban areas, you can see direct reflections. A lot of energy is coming back, and urban areas can be very, very bright. As you have seen in my first slide, I show you that bright areas that was shown by yellow color are more urban areas, while the other areas are really difficult to interpret. So the property image tone, first element of satellite image processing. Image tone is like relative brightness in areas. The image over the urban area, you can see the areas, you can see dark areas, lightly bright areas, and also very bright areas. These images can be very easy to interpret. You can say where the buildings are, you can say where the water is, you can say where the ships are, because you're using the element called image tone, right? So you're using the image tone to interpret this image as a visual interpretation. And then if you look at this particular image over Singaraja area, it's very difficult to interpret. As you can see, this image is taken from a slant view, slant perspective, as it is from a synthetic aperture radar image, and it's very difficult to interpret. So what I want to say is that tone is a very good interpretation element, or tone is a parameter that you can use to process satellite images, but it is not going to work everywhere. So it can fail. So we have to go beyond visual interpretation. Then you have to understand certain elements, few more elements about image. As I said, before processing, you have to understand the image. Now, most of the people who have a little bit of remote sensing background, as you know about the spatial resolution. You have talked about this so many times, but I just put it as an element because spatial resolution is that all these sensors cannot see everywhere on Earth. It can see the smallest area. There is a limit in where it can see the smallest area. So the smallest region that the satellite sensor can see and can be recorded is called the spatial resolution or geometric resolution of that satellite sensor. So you can see that if the smallest area is 30 meter, and there is a house inside this 30 meter area, so what happened? The whole pixel will be recorded by the energy coming from the house. So there will be a number allocated for that pixel. So the spatial resolution or the geometric resolution is 30 meter. That means below 30 meter, like for instance 10 meter, this sensor cannot see. But if you come to the second one, you can see the sensor can see 5 meter squares. So you can see the house is also getting pixel values. So each pixel can be allocated a value depending on the incoming energy or incoming radiation. And also where the house is not occupying, it also can be mapped. So the first pixel had only one DN value, but the second pixel is having 25 DN values because its spatial resolution is much more higher, that is 5 meter. It can see much more small area. And if you go to the next one, it is 1 meter, you can see up to 1 meter area. That means it's like if these satellites, if there is 2 people inside 1 meter, at least you will be able to see 1 person inside that pixel. If these 2 people are standing more than 1 meter distance apart, most probably 1 person will get 1 pixel, the other 1 person will get the other pixel. So you will see 2 dots. That means 2 objects are there. So this 1 meter is the highest high resolution, 5 meter is moderate resolution, and 30 meter is like low resolution. So depending on the spatial resolution, the image capabilities change. You won't see much of details in low resolution, but you will see more than that information in the medium resolution, and you will see detailed information in the high resolution. When it comes to costs, you won't get 30 meter resolution. You can get 30 meter resolution satellite images free, but you won't be able to get 1 meter resolution satellite images free. So they are very expensive. So the first I said about tone, and then I talked about the spatial resolution. It is another element that you have to understand, and you have to understand how it works, and you have to understand why I need, for my case, a high resolution image, or why I don't need a high resolution image, right? So remember, in order to determine that, you have to understand these geometric properties of spatial resolution. Then the second one is radiometric resolution, number of bits that a particular image can record. So if it is an 8-bit image, it can record up to 0 to 255 DN values. That means each pixel can have 255 values for an object it is looking at. And if it becomes 9-bit, much more higher radiometric resolution, it can have more gray levels. 16-bit, more gray levels, and 32-bit, it's large amount of gray levels. As you can see in the left side, it's just this 1 byte. That means only black and white. But on the other side, it is 16-bit. You can see buildings with different colors even. But in the left image, you can see all the buildings are white and the rest of are black. So only 2 details you can see. Some are white, some are black. So only 2 details because it has only 1-bit image. It's only 2 gray level values each pixel can record, either 0, either 1. But in the 16-bit case, you can see it can record 65,536 values for each pixel, higher radiometric resolution. So you have to understand, for my case, for my processing, why I need a high radiometric resolution. If you're working in urban areas, of course, you need a higher radiometric resolution. But if you're working in a forest area, maybe you might not need a high radiometric resolution. Why? Because most of these areas are vegetation. Vegetations, if you can represent it by 8-bit, it's more than enough, right? Or otherwise, if you want vegetation and non-vegetation, even you can get 1-bit radiometric resolution because only 2 information that is necessary for you. Right? So you have to understand the second element, radiometric resolution. And when it comes to temporal resolution, so each satellite, most of these imaging satellites are not geostationary. They are sun-synchronous. That means they go close to the polars and revisit the same area at a particular time. So for instance, if you take the Japanese JAXA ELOS pulsar, that means L-band synthetic aperture radar ELOS sensor carrying L-band synthetic aperture radar sensor, it comes to Colombo today, and again it comes to Colombo after 46 days. So if it comes to Colombo today, for 46 days, you don't know what happened in Colombo. After 46 days, 𝐴𝐿𝑂S comes back on top of Colombo, an image. So you will have two images, one today and one after 46 days. Right? That is temporal resolution. But when it comes to TERASA, that means German DLR, German Space Agency X-band synthetic aperture radar, it has much more higher temporal resolution. It comes to Colombo today, after 11 days, it will capture Colombo, right? So you will have details of today, and after 11 days, what happened in Colombo, you will have two. And if you come to Cosmos SkyMed from US, it has a more rapid acceleration. Because of that, it comes to Colombo after 12 hours. So that means if it comes in the morning, after 12 hours, in the evening, it will come back to Colombo. So it has more high temporal resolution. Right, so hope you understand that. So basically, you can see if I have 𝐴𝐿𝑂S 46 days, most probably between 46 days of 𝐴𝐿𝑂S, I will have 3 TERASA access, right? So for 𝐴𝐿𝑂S, I will have only 2 images, but if I use the same period with TERASA, I will have 3 images. So you as a scientist or a researcher doing satellite image processing, you should understand how much of temporal resolution I need. So if somebody is actually working on, say, change detection, a rapid change detection. For instance, say you're monitoring a very rapidly changing phenomenon. For instance, say COVID patients. Now, if there is a way that you can map the distribution of COVID patients in Colombo, of course, you need another image as soon as possible. You can't wait 46 days. You need a second image much more quicker, right? Because you know how rapidly COVID is spreading. So if you can interpret the amount of spread using a satellite image, of course you can do, but it needs a little bit of hard amount of work. You need a very high temporal resolution. But if you're monitoring some other phenomenon, for instance, if you're monitoring the construction of a highway, of course, you know, a highway cannot be constructed like 10-15 kilometers within 11 days. It's not possible. So most probably 𝐴𝐿𝑂S might be okay because you want to see what happened to the highway. Is the construction is going on smoothly, so 46 days might be enough. So depending on your application, on your objective, the need of the temporal resolution, right, is very important. So I want you to understand those. Now I said spatial resolution, geometric resolution, and I said the radiometric resolution as well as temporal resolution. Then the next one element that you have to know is spectral resolution. I said in the start that remote sensing can be divided depending on the sensors where it is working on the electromagnetic spectrum. So when you take a satellite image, I said this image has a pixel, it has a DM value. And also, the satellite can produce images or set of pixels in each areas of the electromagnetic spectrum. Some satellites can image in green region, blue region, red region, infrared region, near infrared region, shortwave infrared region. So depending on these regions, they produce images. So for instance, if you take Landsat ETM Plus, you can see there are 8 bands. One is blue-green region in the electromagnetic spectrum. You can see the wavelength on the x-axis and the reflectance. That means the energy coming back, right? So blue-green region, it has images. In green region, it has images. Red region, near-infrared region, shortwave infrared region, thermal infrared region, and again another region of the shortwave infrared. So there are 2 shortwave infrared regions, different wavelengths. One 0.55 to 1.751, and the next one is 2.09 to 2.35. So different regions of the electromagnetic spectrum can be imaged. So spectral resolution means how many images can be produced. In simple terms, how many images can be produced across the electromagnetic spectrum. So if the Landsat has 8 bands, and the span is actually the region from 0.5 to 0.9 micrometers, that is more or less a little bit of large spectral region, because the pan is always having a higher spatial resolution. So because of that, a small area on the ground cannot be imaged if the incoming radiation is small. So you need a little bit of large area in the wavelength to get enough energy back to give an energy value to the pixel. Mind you, I won't tell you, if somebody wants to know detail about these things, I kindly request you to listen to my previous lecture, which I did last year, where I'm talking about all these spatial and spectral aspects in detail. But here I'm just trying to give the idea where you can use this as an element to understand how it can be important for your satellite image processing. Right, so you have, say if you have 8 bands, it's like 7 bands in the respective regions, and a panchromatic band in a little bit of wider electromagnetic region, especially in the visible region. So you can see the pan band is always in the visible region, not in the near-infrared region. So the span or the panchromatic band is always having a high resolution. So these bands will have a spatial resolution of something like 30 meter or 60 meter in the case of thermal. And in the case of pan, it may be like 10 meter or maybe 15 meter or maybe 2 meter. Okay. So you can see the spectral region that the Landsat is mapping is from the blue-green to near-infrared. So you will have a spectral profile for vegetation. Now, each object on the ground behave differently in the electromagnetic spectrum. Vegetation behave like this. So basically vegetation, if it hit by sun, the electromagnetic energy in this region will be having reflectance something like this, and it grows higher in the near infrared region, and again it goes flat in the shortwave infrared region. So this is the identity of vegetation spectrum or vegetation objects, the spectral profile we call it. For soil, it's like low reflectance in the visible region, but very high reflectance in the near-infrared regions. And for water, high reflectance in the visible region, but very, very low reflectance in the near-infrared region. So basically, if you take a near-infrared image, water will be black because there is no energy coming up. Vegetation will be red, very high. Soil will be medium tone. Relative brightness will be little low than vegetation, but very high than water. So you can see, you can compare these 3 elements across the spectral regions or electromagnetic spectrum. This is called spectral resolution. The spectral resolution is number of bands, very simply said. So the amount of number of bands going to be more, the spectral profile is going to be very much better. For instance, if you take this Landsat ETM Plus, like Landsat 8, it can map 2 more regions of the shortwave infrared region. So if you plot the spectral profile of vegetation, you will have the profile around visible region, near infrared region, as also shortwave infrared region. But you will not have any information in these regions. So because the sensor doesn't make any images in these regions. It makes images only in the regions where it can see an object or collect energy coming back. But when you go to hyperspectral sensors, where the spectral resolution is very high, it can image or make an image in most of all the regions of the spectrum, all the electromagnetic spectrum. For instance, you will see a complete spectral profile of vegetation object, right? You can see, because you saw that in Landsat, you saw that there are no information in this region, no information in this region, no information in this region. But when you go to the very high spectral resolution Earth Observation 1 Hyperion from NASA, right, you will see a continuous spectral profile. Why? It has 220 images, right? While the case of ETM plus, it's only like 10 bands, right? And panchromatic only 1 band. But in hyperspectral sensor, you can see 220 bands. So what happened with hyperspectral sensors? They give a complete spectral profile because there are 220 images across the electromagnetic spectrum. Okay? Across the electromagnetic spectrum. Right? So Hyperion is a hyperspectral image where you can get images for very small regions of the electromagnetic spectrum. So for instance, if Hyperion to have 220 images, just imagine how small areas it is detecting the incoming radiation. Very small areas. So working with hyperspectral sensors are very, very important for geologists, where you want to find minerals. If you want to find oil in the sea, right, you can work on hyperspectral images. Why? You know, if an area is occupied by minerals, each mineral behave differently in the electromagnetic spectrum. What I'm saying is, you get a blue sapphire and a red sapphire, and you hold it to the light, and you try to get a picture. You will see that the blue sapphire is pictured in a different way, and red sapphire is pictured in a different way if you image them in infrared region. Why? Because you know, sometimes the blue sapphire is not reflecting energy properly in the infrared region, while the red sapphire is very with a very high frequency, it is reflecting energy. So they are imaged in different ways in the infrared region. So directly, if you are a scientist, you will definitely say, this is, by looking at the image without looking at the objects, this is a blue sapphire image, this is a red sapphire image. Just the same way, if a satellite passing on top of the ground and it images these minerals with a hyperspectral sensor, it will be able to show different objects on the ground based on their very high spectral resolution. So you as a scientist, if you want to process data, you have to understand, do I need a high spectral image, or don't I need a very high spectral image? If you are an urban area scientist, you don't need high spectral images. But if you are a geologist, you will need hyperspectral images. So you have to understand this concept of spectral resolution. What you can see here is a hyperspectral image of Earth Observation 1 from one of my work in 2008. This is the vegetation patch close to the Forest Research Institute of Dehradun, India. Right? You can see the spectral profile on top of vegetation. As you can see, once it is not corrected for atmosphere, it will be like something like this. But if you collect it with the atmospheric atmosphere, you will see the red edge, very famous phenomena for vegetation. Lush vegetations will have a red edge, right? So the spectral profile is continuous because this is a 220 band image, right? This is a false color composite. I will talk about what is false color composite. I'm using for band 40, band 30, and band 20 on RGB. That's why it is showing RGB colors. But remember, this image has 196 bands. Why? Out of 220, I had to remove several bands because in Hyperion sensor there is an effect called smiling effect because it works in very small areas of the spectral electromagnetic spectrum. It cannot get the energy properly, and in that case, in some images will be blurred or has an effect called smiling effects like small dots. So those images cannot be processed and they have to be blurred. Okay, right. So now I'm just shifting a little bit to visual interpretation. I talked about tone, I talked about spatial resolution, radiometric resolution, just the spectral resolution and temporal resolution. Those are elements that you need when you're interpreting an satellite image. As I said in the beginning, I said before processing, understand the image. To understand the image, you have to understand these elements. If you don't know these elements, you don't understand your image. Then, though you can be very good in processing, but you don't know what you're processing and what are the information actually you can get. You will apply very advanced techniques, but you won't get any result because the image properties are different. So, though you try very advanced techniques, there is a limit where a low spatial resolution image can provide. There is a limit where the high spatial resolution image can provide. There is a limit of a high spectral resolution image can provide. There is a limit a high temporal resolution image can provide, a low temporal resolution image can provide. So there is a combination of these four elements, vice versa. It makes a complex scenario of the image. You have to understand bits and pieces in order to process it correctly. Now size, as you know, this is an element. If you can take this particular visual element size, especially for this, the high resolution images, by looking at the size, you can say this is an object by man-made objects. While looking at the shapes of the other forest elements, you can say this is natural element. Likewise, size can be used to distinguish objects. So size is a visual element, and most of the time, maybe you will be able to write a code so that it runs on top of the image, searching for rectangular size, rectangular shape objects with rectangular sizes. That means a square area, right? So it's a qualitative. That means it's most of the time it is not quantitative. So size is more visual, an element used for visual interpretation of satellite image processing. Shape is the same. Different shapes tell us different objects, but mostly we use these elements for visual interpretation. Texture, it's a pattern. This is very important. Not like shape and size. Texture is something different. Periodic variation of gray level values. That means how the values on pixel change periodically. That is basically the definition of texture. But remember, this term texture is very important term. If you have a satellite image, you can turn that satellite image into texture image. So remember, original satellite image is something like this, what you see, right? You will see grass, you will see forest, you will see man-made structures, you will see roads. But when you convert it into texture, like you see in the other side, you will see different patterns of gray levels. Remember, so just to understand texture, original image and texture image is something different. You can convert the original satellite image or the real satellite image into texture image depending on your need. In that case, you have to use advanced texture properties. For instance, you can use gray level coefficient matrix, Moran's-I, 𝐏𝐫𝐴, 𝐏𝐫𝐴𝐷, multiplicative autoregressive random fields or Markov random fields, I'm not going to talk in detail, but just I want to show you, this is one from my work. You can see texture is a neighborhood concept. That means a particular pixel, how it is related to its neighborhood, is what texture is all about. Just for now, as I have to talk about in detail of many things, I'm just leaving you to think about texture a little bit more, read about texture a little bit more if you're really interested in. You have to understand you're processing images on top of Earth. Satellite images are imaging objects on the Earth's surface. So if there's a set of buildings, of course, there should be a road close to that. There should be a river. If there is a forest, of course, there should be a fence. Right? You can understand relationships are there outside. In a very urbanized area, you can't find a forest. That is what nature provides us. So these neighborhoods are patterns. They have relationships. If there is a building, of course, there should be another building close by. So if there is a pixel belonging to this building, the next pixel should also most probably be a building, not a forest. Right? So you have to, if you can give values to the original image for buildings and roads and rivers by use of some sort of a methodology, some sort of a mathematical model, then you're converting your image into texture elements. So you do whatever you like on that texture image. Okay, so texture is very important concept. So you can see what I'm saying is like this a paddy field and close by is some area. So you're looking at a pixel and its neighborhood. So you determine the texture. So texture is like, if I put these things, it's like, what is it? It's a circle inside a rectangle, right? And the context, it's a knife, fork, and a plate. What I'm trying to say is that on top of a dinner table, you're not going to find washing items. It's the context, right? So in a dinner table, you're not going to find cooking utensils. It's about food and eating. So the context, it's just the same. So images shows us context. We have to understand that concept, right? So if there is a circle inside the rectangle, you have to say it's like inside the Western province, you have the parliament. It's not the parliament outside Western province. It's the context. We know that about Sri Lanka. So this is much more close to the concept of topology in GIS. So remember, patterns, contexts, patterns, paddy fields, rivers, and all these are elements. Okay, right. So just up to now, what I said is elements. Important for you to understand. I talked about resolutions. I talked about tone. I start with tone. I talked about resolutions, and then I talked about shape, size, visual elements, and then I talked about texture, and then I talked about patterns, the context where I'm working on. Right, those are very important when you're working or when you're doing satellite image processing. And now I'm shifting a little bit towards something as a tool that we use in satellite image processing, the histogram. What is it? You have an image. Each image pixel shows a different value. And depending on that different value, it has a color. Like, for instance, you have an image. These are the pixels. It has a spatial resolution. It has a temporal resolution. It has a radiometric resolution, right? And the spectral resolution, also it is there. But if you take one band, there is no spectral resolution because spectral resolution is number of bands, as you say. So here you can see spatial resolution. That means what is the size of the pixel. And radiometric resolution, what number of gray levels are there? Red, green, for instance, red, here green, dark gray, and white. So it's like 4 bits, right? You can have 4 values for that. it's like 2 bits to the power 2. You can have 0, 1, 2, 3. So 0 is like gray, 1 is like white, 2 is like red, 3 is like green. So those are the values represented by different colors. So if I plot the colors with number of pixels, you know the number of red pixels in this image is 6, 6, 12. And number of gray pixels, 15. Number of white pixels, 15 again. And number of green pixels is 8. Just a simple plot. It shows us how these particular gray levels or particular pixel value, how it is occurring, right? How it is occurring. Number of times the red occurred is 12, number of times the gray occurs is 15, number of times the white occurs is 15, number of times the green occurs is 8. So if I ask you, what is the gray level which is mostly occurring in this region? You will definitely say, looking at the histogram, it's the gray pixels and white pixels. So if the gray pixels are belonging to buildings and white pixels are belonging to grass, you will say this area has more amount of buildings and more area of grass, right? And less area of water. Say the green is belonging to water. Likewise, the distribution of the pixels, so which we call histogram. Histogram is a tool for satellite image processing. So looking at the histogram, you can say a lot of things. So looking at the histogram is very important. And if you take a satellite image, the histogram is its distribution. Most of all, if you take optical images, the distribution will be a Gaussian distribution, right? So what it says, there is a pixel value that is very highly occurring, and there are pixel values away from the mean value that is occurring less in this image. That is the Gaussian distribution, as we all know. So this is histogram of this image. And because it's a continuous distribution, we can call it Gaussian normal distribution. But if it was a discrete distribution like this, it will be a histogram. So the image histogram is its probability distribution. So it can be Gaussian for optical images and gamma distribution for radar images. Basically, in optical images, you will see mean value and the standard deviation both sides. But in radar images, you won't see mean values and standard deviation. There is a value that is occurring very highly, and then it's exponentially decaying because this gamma distribution is negative exponential distribution, right? So you will see a distribution like this. Now, this will be a little difficult for most of you to understand if you have never worked in satellite image processing. But remember, at least if you don't get this Gaussian and gamma distribution, you should be able to plot the number of pixels in a histogram. Then you will see a distribution. What is this distribution? It is more like a Gaussian distribution because there is mean value and a standard deviation. That means mean value is the value somewhere here, the data value, the pixel value, which is very highly occurring, and the pixel values which are away from the center. So it's like more or less a Gaussian distribution. So basically, histogram is distribution. And looking at the distribution of your image is very, very important in satellite image processing. So histogram is like looking at your image in a very different manner, in a very summarized and composed manner. So always when you're doing image processing, try to generate a histogram for your image and try to understand which DN values or which pixel values are most highly occurring, which pixel values are not occurring. So if you want to extract pixel values which are not occurring from the image, you're blindly processing the data, but you won't get a result because there are no pixel values belonging to what you want in the image. So if you just plot a histogram and understand your pixel values prior, then you know what to process, what not to process. So remember, histogram is a very important concept in satellite image processing as well as in other sciences as well, because distribution says a lot about what is happening. So we know in probability, actually, sometimes what we want is basically the most occurring value, the highest probability value. So that is what this program is showing you about. I hope you understand, and I hope you all are in, right? Everybody's in. Just give me a shout, someone.
Yes, sir.
Okay. At least that is an encouragement, because I'm just like talking to thin air sometimes. Okay. So you can understand that this is a very large area, and I'm talking about this large area, and it takes a lot of effort for that. And there can be confusions if you have not done any remote sensing. But you asked me to talk about satellite image processing, so I have to talk about satellite image processing. At least I'm trying to give you a cross-section so that you can stick to each section and improve your knowledge. So when you go to those elements have passed, I talked about spatial resolution, I talked about the resolutions, I talked about tone, I talked about the elements of visual interpretation, size, shape, and patterns, texture. Then I talked about a tool which we can look at the image, that is histogram. And then I'm finally talking about the storage. So satellite images are very large. They're very large, right? I will show you in my last slide an image of Sri Lanka. It's a mosaic from synthetic aperture radar, which is like 93 GB. It's just a JPEG image, right? In the end, once you process, but the original image is 93 GB, right? So satellite image processing is very, very difficult because the consumption of its storage, the consumption of each image in the storage. So basically, you see satellite image is number of pixels and number of bands. So it's a multi-dimensional image. It has pixels in green region, it has pixels in blue region, it has pixels in red region, near infrared region, shortwave infrared region, thermal infrared region. So bands, one dimension is band. And also it has X and Y directional pixels, X direction, Y direction, and the third dimension is bands. It's spectral resolution. So you have an image from a satellite, red, green, and blue. Just think there's only 3 bands and some pixels. And if you ask me what these pixel values are, it's the number allocated for the incoming radiation. If the radiation is large, you will have a large value allocated from your radiometric resolution. If it is 80 bit, if the radiation is coming from building, most probably you will see the pixel is white. That means it is 255. If the energy is coming from water, the pixel is black. It doesn't have any energy. As I showed you, all the energy is absorbed by water. So it will have 0. So in an 8-bit scale, the pixel value 0 represents water bodies. Pixel value is close to 255, 255, 254, 253. If you plot the histogram and you see 255, many number of pixels of 255, that means your image has more number of pixels belonging to buildings or areas which reflects energy very highly. Areas which reflects energy very highly is called impervious areas. That means tar, that means roads, very highly reflect. Mirrors, that means glass, concrete, the brick walls, the tile roofs, they all reflect energy very highly. So you will have white pixels for these areas in a grayscale. That means 255, 254, 253 like this, right? But for water, it will be 0, 1, 0, 1, because no energy is coming back. Right, so basically, there are three ways that we store this incoming radiation. Band sequential form, that means the whole red image and the whole green image. You can see in a sequence. That means red, first row of the red image, 147. And then continuously first row of the green image, first row of the blue image, and then it goes to second row of the red image, second row of the green. Likewise, it goes. That is basically band sequential one, right? And there are advantages, disadvantages of BSQ. And band, interleaved by lines, you can see red image first pixel, and the green image first pixel, blue image first pixel, right? And there is a line passed and it becomes the second pixel after line 444, again 777. Likewise, it goes to the second pixel, a line passes 555, a line passes 88. And also band interleaved by pixels, as you can see, first pixel of the red image, and the second pixel of the red image, third pixel of the red image, fourth, fifth, sixth. So it finishes the red image, finishes the green image, finishes the blue image. As you can see, once you plot these things, their storage is different, right? You can see by looking at the pattern of red and blue, you can see they are different. They're different. They have their advantages, they have their disadvantages. So most of the time, BIP format is very famous, band interleaved by pixels. And you know why certain storage, especially people in computer science know why we choose different storage mechanisms, because we want to access them very quickly. And maybe we want to write them or write them very quickly. Maybe we want to store them very quickly. So depending on that, the storage depends. Now these are the three formats of storage formats that we use in order to store satellite images. Now I'm going directly into a little bit of satellite image composites. That means we can combine bands. So we call it composites. Remember I showed you a RGB composite of Hyperion. I said red band is 40, blue band is 30, and the green band was 20. Remember RGB, it's a composite. What happened in these composites? Say you have 4 bands. Blue, there is an image. For green spectral region, there is an image. Red spectral region, there is an image. Near infrared region, there is an image. So you can see they are different in grayscale. Slight differences are there. In the near infrared region, you can see the vegetation patch is very high, while the paddy fields are very bright, right? And but the other images, they have slight gray level changes. So we can combine them in RGB, because what we see is RGB in the computer screen. So if we put blue, green and red, red into red, green into green, blue into blue, you will see a normal image. We call that is true color image, true color composite. That means red is given to red, green is given to green, blue is given to blue. So you will see a normal image. You can see the vegetation green, buildings in this area. There is a ground here, and there is a path here, car track, and there is a road here. You can see that. It's true color. But if we change the composite, what we do is we give near infrared for red, red for green, and green for blue. This is a change. What happened now? Near infrared band is showing the red color. So what we see by red is always vegetation, right? Lush vegetation will be bright, while the soil and all where there is less amount of vegetation will be more or less to green and blue color, because near infrared is now in red band. So this is a false color composite. This is a true color. This is a false color. Why? We are changing the combination. We are changing the composite. This is one very important band manipulation technique that we use in satellite image processing to get information. For now, I'm just moving forward. You can always write to me if you have questions why we are doing this. In order to understand why we are doing this is that if we want to show near-infrared reflectance in red color, we do this, right? Diminishing the red and green effects, we want to highlight near-infrared, so we give it to red band. So most probably, we will see red color for vegetation patches, right? So this is kind of technique that we use, composites that we use to showcase, manipulate the electromagnetic spectrum and show the image, right? We do this manipulation for radar images as well. In the case of radar images, we don't have red, green, blue. We have X-band, L-band, P-band, depending on the wavelength. Now I get stuck because you might be asking me what is these bands, L-band and P-band. I will just leave it right now. I will just stick to this. I will just leave it for you. One day you will understand what I'm saying. X-band is short wavelength. L-band is much more bigger wavelength. P-band is much more larger wavelength. And very high frequency is like 3 meters. Just imagine wavelength is the distance between peaks or toes of the electromagnetic wave. 3 centimeters we can measure, something like this, the wave, the peak, the distance between peaks. 27 centimeters, the distance between peaks. 70 centimeters, it's almost like 100 centimeters. You can measure the peak, the distance between peaks. 3 meters, the distance between, it's a very long wavelength coming from the satellite and hitting the ground, right? What happened? When it hits a tree, X-band, because it's short wavelength, it will map most of the areas of the tree. L-band, because it has longer wavelengths, it penetrates the tree a little bit, so most probably you won't see the leaves. And a P-band, it's very large wavelength, it goes across the tree. And VHF, it's just can't see anything, it just goes through the tree. Penetration. And once we get those images, we can combine, right? X-band image, C-band image, L-band image, combine them, we get a composite. Just get the idea, composite is a combination of different bands. And the way we combine shows a different information. We can combine optical images bands as well as radar images bands. Optical images, it's green, blue, infrared, shortwave infrared. But in radar images, it's X-band, P-band, L-band, V-band, and also it depends on the polarization. It's a completely different area and very complex area, but their properties are different. So I'm just not going to confuse you with that, but composites are a combination of different bands, different spectral information to show us a different map, right? So remember the term composite. Now this composite, red is X-band, green is L-band, blue is C-band. This is the composite. And if we give red X-band, green L-band, and B the X-band again, we will see different information. C, the river, the lake is different color in different composites. So remember, just get now, leave everything. Composite shows us different images, satellite images, information. So depending on the combinations, we can extract different information, right? Okay. And prior to going a little bit further, just to clarify out, you use land cover, land use. What are the term shows? What are the term says? Land cover is the actual cover of the land, earth surface, water, forest, soil, land cover. Land use is what is the purpose forest is being used to. Maybe vegetation, then it's paddy. Paddy is land use, it's not land cover. Okay. Urban areas, it's land cover, land use. Why this area is being used for urban area? this area, which was a land cover previously, now it's an urban area, the usage of the land cover. So land cover, land use, just figure it out. Now I'm going to the first part of, you will get scared when I'm going to finish this, right? But just keep listening. I am tired, not you guys, okay? So just first one, classification, and then I will just go very quickly. Just putting what is necessary for you. Okay, sorry about that. Yeah, everybody's there. Anupa, are you there?
Yes, I am here.
Okay. Right, I'm not going to give you a time to ask questions, but I will give you at the end. So first thing, I talked about a lot of things up to now. They are general matters which is needed in order to talk in the language of satellite image processing. Very briefly put, summarize. But they are very in-depth areas, each and every one. If I talk about composites, you have to learn a little bit more. You have to dig in deep, because this is a very, very large area. If you talk about spatial resolution, you can do research in spatial resolution improvements. You can do research in radiometric resolution improvements. You can't do research in temporal resolution improvements. Why? You have to join NASA or ESA or JAXA and make satellites in order to do that, okay? So making the satellites to come back very quickly, it's like building a car with very fast capabilities, right? So you have to become a satellite scientist. Unfortunately, we don't have satellite scientists in Sri Lanka, but there were some few satellite scientists in Sri Lanka. That work with China, I don't know, right? So these areas you can work on. The first thing I want to talk about, classification. Classification, the term means classifying an image for information. You have an image, you have bands, that is the satellite image, may be stored in BIL, BIP or BSQ formats. You can convert it into TIFF, JOTIFF, JPEG, the other imaging formats you can convert. Okay, don't worry. The original format may be BIL, BSQ, BIP, but you can convert it into TIFF, JOTIFF formats and work on them. JPEG, PNG, right? You can convert them in and then work on the images. They become very light when you convert them into those image formats, but you have to be very careful, because remember, these are not pictures, these are images. Each pixel has a location on the surface of the Earth. So most probably, you have to, when you're converting these images into some sort of imaging format, you have to understand these images carry coordinate system information. That means you get an image, you process it, and if you put it into Google Earth, it should go, if you work in Wilpattu area, and then you do everything and put it into Google Earth, it should go to Wilpattu. It should not go to the USA, okay? Right? You'll understand. So there are a lot of things to learn about geometric properties of an image, but I leave it so you can understand it's not easy to talk about some of the image processing in one guess. It's a long, large area, but I'm just trying to put it briefly so you will think and you will orient yourself into areas where you have to work on, you have to search more, you have to learn more. So what we do is we get images, we have bands, and I said these pixels have DN values or digital numbers. That is what we call the pixel value. And they depend on the radiometric resolution, 8-bit, 16-bit, 32-bit. What we do in classification is assign these pixel values or DN values a class. First pixel is assigned forest. This pixel is assigned urban. This pixel is assigned water. What happened? Your image is turned into a classification. Urban area, forest, and the water area. How can we do this? It's not easy, as it says. So classification is one of the main areas of satellite image processing. We do classification. We use land cover classification or classification techniques. Remember this technique. This is classification. You use classification to convert an image into information. This is how most of these survey department maps, most of the time, are being generated recently by satellite image processing and using land cover classification. So by using land cover classification, you can convert these satellite images into useful information about land cover and land use. Sometimes you can classify the satellite images based on minerals, convert it into mineral types, convert it into geological types, convert it into soil type. So all these conversions into real information is coming under classification. It's the area where in satellite image processing where we talk about assigning pixels classes. Now this is an example of some classifications. This is a Avenue 2 image from JAXA. It's an optical image of 2.4 centimeter resolution, and you assign classes for that. This is on top of Fukushima area in Japan. Very advanced mechanisms have been used to classify this image. I used for this fuzzy C-mean clustering and fuzzy marker-random field models, conventional marker-random field models as support vector machine-based classification to classify this image and do a comparison. Why I'm talking about these advanced methods? I generated new classification methods and I wanted to compare it with standard methods like support vector machines. So you can see what I did is that I used 3 classes. I used 4 classes: paddy, residential, industrial, and trees. And I try to classify this area into those classes. And this is what I got. So basically, if the number of classes are more, the number of information is becoming more. And you can see that support vector machine has much noise, but in marker-random fields and support the fuzzy-based marker-random field models has reduced the amount of noise due to point spread function effects in satellite images. So there is a lot of noise in satellite images. You have to deal with them in satellite image processing. So it goes on. So classification can be divided into unsupervised and supervised, and also parametric and non-parametric methods. So not going into detail, but just remember, if somebody asks you what are the classifications, there can be supervised classification and unsupervised classification. Most of the people who have done remote sensing by now know what I mean by supervised and unsupervised classification, and also non-parametric and parametric classification. All these classification methods in satellite image processing are developed to assign pixels information values. We call in computer programming this is coloring process. Giving a pixel a class, giving a pixel a feature, giving a pixel a detail. That is what we do in class. So to do that, we use probabilistic methods, parametric methods, and non-parametric methods. We can just cluster them, put them into a scatter plot, and cluster the pixels and say this is one class, this is one class, this is one class, and do a classification. Or otherwise, we can just look at the histogram and say, okay, the highest value is this value, the median value is this value, the lowest value is this value. So cluster this into 3 classes and you will see classes. Likewise. So this is a concept for, I know most of the students who learn remote sensing in my faculty, they take classification very lightly. Because if you use a standard remote sensing package, it's very simple, click. You get the image, you do the initial processing, put it, and then just click on maximum likelihood or k-mean clustering or something. You will get the image classified and you are satisfied. I have done a classification, but it is not the case. You have to understand the theoretical concepts. If you go on understanding the theoretical concepts, these are very difficult areas to understand. But remember, one main area of satellite image processing is satellite image classification, where classes are assigned, and these are the most common classification techniques, isodata clustering and k-mean clustering for unsupervised classifications. For supervised classification, maximum likelihood, minimum distance, k-mean is artificial neural networks. Now remember the difference between these two is unsupervised classification. We put the image into the computer and we ask him to cluster it. And it doesn't depend on our inputs, it's just cluster, right? Using isodata or k-means. Right. Not going into detail because if I'm have to talk about that isodata clustering, maybe it's 3 or 4 hours lecture. K-mean clustering, maybe 2 days of lecture, right? And then if you go to supervised classification, in supervised classification, I supervise the classification. I say this pixel is for us, this pixel is building, this pixel is water. You classify, and then it gives me the classification. So maximum likelihood, minimum distance. Most of the time, it's probabilistic. Parametric methods. Again, we divide these supervised and unsupervised into non-parametric and parametric. In the parametric case, we use probabilistic approaches, and the non-parametric case, we use geometric approaches like support vector machine, random forest, artificial neural networks, and nearest neighbor classifications. There are advanced classification mechanisms like spectral angle mapper, linear spectral mixing, super resolution, marker random fields. So we can understand, if you want to know in detail about classification, each classification you have to study by yourself and to get an understanding how it works on an image. Okay, so classifications are daily, it's updating. So basically pixel-based classification can be done and object-based classification can be done. We will look at, what we can talk here is pixel-based classification, object-based classification, I will talk in the end. But the second one in satellite image processing is change detection, finding changes between satellite images. Okay, finding changes. I have only half an hour more. I will try to reduce it. Okay, changes between days. There can be subtle changes, abrupt changes. Changes we want to understand using satellite image processing. This is one of the areas that we work very, very largely. For instance, if there is a disaster, we want to know the change. What happened before the flood and after the flood? What happened before the forest fire? What happened after the forest fire? Right? So the disaster can be natural and human causes. So we want to know the damages. Damage is a change. Change is a change. Right? So we want to know the changes. This is a change of Colombo, as you can see very, very lightly. After the COVID-19 first lockdown, you can see the soil areas are becoming vegetation because humans are not there, and more red color is penetrating in this composite. As you can see, this is a color composite where the RGB is band 832. So this is a false color composite. So band 8 goes to red, band 3 goes to green, and band 2 goes to blue. So red color shows basically the near infrared and shortwave infrared region. That means vegetation are the highest, having the highest spectral reflectors in this region. So vegetation is highlighted. So this is a change happening. Type of changes, short-term changes, cyclic changes are there, directional changes, multi-directional changes, right? So you can read about this. I will just pass on this PDF for you. Right, unwanted changes, we don't need phenological changes. So if we don't want to know the phenological changes, that means how the color of these trees are changing, but to know what happened on the ground, then we will have to correct the exact date images. And changes due to sun angle, that means in the morning and in the evening. We don't want changes happen because of the sun's position. It's an unwanted change. So for that, we can do the radiometric calibration, similar incident angle, similar time of the day images. So they are not changes that we want. We want the changes from these kind of effects, not the changes coming from this, right? Sun angle, atmospheric effects, changes due to atmosphere we don't want. We really want what is happening on the ground. So if there is a change in the image because of atmosphere, we have to remove it to get the actual change. So we do a radiometric calibration. Due to geometric, for instance, these two images are not geometrically aligned. So if I do a change, it will show me that this road has a change. But you know that this road is the same road and there is no change here. So in order to avoid such changes being occurred, we have to align these images correctly. So we do geometric corrections into the image. That means co-registration and all. Right. So this is the change detection techniques developed in remote sensing. You can see how much of people worked in change detection areas and how much of mathematics and statistics gone into this change detection methodology development. So this is the real satellite image processing process. So changes can take from just dividing images. Changes can do by using a vector between two pixels and seeing how this vector is changing. Just dividing the two images, you can get the change. Right? Ratio is that. And also band composition, just like using different bands together, you can direct the changes. I said composite is like false color composite or true color composite. By manipulating the bands, you can get the changes, differences, right? And also by doing transformations like principal component analysis, basically if you put two bands, one band and the second band, you see that they are agreeing very well along this axis, but they are not agreeing according to the perpendicular axis. So we transform this by using a principal component transformation. Then what happened along this axis, changed pixels will be shown to us. Pixels that has changed doesn't have a very high correlation over the axis of the highest variance. So these are the things that you can take to do change detection. As you know in statistics, if you simply plot two bands, if you do a regression, you know that they should agree if there is no change. But if there is a change, they are not going to agree. So several pixels which are not going to agree will be away from this regression line, so you can just detect them. And also classify one image, classify another image. You can see the land use classification and find the change between them. Post classification, change detection, right? And also temporary trajectory. That means during the time period, you just plot land cover pixels and see in the year 1 how they are their frequency, and in the year 2 how their frequency. So if it is a forest, if the frequency in the first year is very high, and the range between the maximum and minimum is very high, but in the second year, if the maximum and minimum range is very low, that means, of course, this land cover has been diminished. That means there is certain amount of change. Somebody has cut the forest. Okay. Right. The third one, I talked about classification, change detection, data fusion. What does it mean? Fusing different images together. Hyperspectral with multispectral optical images. Hyperspectral with the radar images. Radar images with the thermal images. Fusing different images to get information. What we want is information, not the image. So how can we do image fusion? We take several images, fuse them at pixel level. We take different images, extract features. That means from the first image we extract forest, second image we extract forest, third image we extract forest, only get the pixels of the features belonging to forest, fuse them, and we will get feature level fusion. And decision level fusion. We get the forest and then we do a decision. What? We want from the forest the pixels which has, say, now there is a forest. You extract the forest pixels. And you know in the forest there is some sort of a disease. Because of that, one part of the forest is dying. So you want only the dying pixels. So you identify the dying pixels. That is a decision you do on the forest pixels and fuse, and you get the result. So fusion can be done. But the fusion is happening at different levels. Pixel level, feature level, and decision level. Up to now, just remember that, okay? Normally the general workflow, if you have a radar image and a multispectral image, you know in the beginning of the lecture, I said that their geometry are different. So we want to fuse them. We do a system correction, we do noise reduction, we co-register, and we fuse. And we get the image, right? I will just replace this fusion methods, but just to, I will take one or two, not everything. Just see, we have red, green, blue images. We convert it into intensity, hue, and saturation. We replace intensity by pan image. You know, pan chromatic image is a different band. It's high resolution. We fuse it here. We replace the intensity by pan image. That is the fusion. Convert it back to RGB. So this is a color-based fusion, not very effective. Now here, a principal component. We convert the image into principal component 1, 2, and 3. Say it is 3, right? Then the first principal component is replaced by another image, and then retransform or inverse PC transformation to get the set of images. This is another type of fusion. Another fusion, you get the band 1 DN values and divide it by the band 1 plus band 2 and band 3. Divide band 1 pixels with the total of band 1, 2, and 3 and multiply it by the digital numbers of the band you want to fuse. Another image, take another image and multiply with this ratio. You do a fusion. So you can see, you have to understand is that you're combining different images. That is what we do is fusion. You can use artificial neural network. I know most of you who are in computer science use artificial neural networks. You can do image fusion using artificial networks as well, and also by using fuzzy logics. I'm not going to go into detail because this is one of the very famous or very recent area of mathematics, fuzzy logic, that deals with uncertainties in objects, right? By using membership grades. So you can use that. That is fun. And also Bayesian fusion. Say there are a number of sensors, convert them into conditional probabilities, and now I want to get a particular feature. So I convert this image into probability, conditional probability, depending on the first feature, second class, and the third class. Say there are only 3 classes, okay, not n class. So I do this, and then I get the conditional probability when all these classes are happening, and it's a fusion. So number of images in a Bayesian framework, in a conditional probabilistic framework, we fused it. So fusion is a satellite image processing technique. Very advanced, very powerful, but need a lot of hard work. You can combine any number of images. Okay. Last one. You should be really tired now. Yes. Guys, you're there. Anupa, you're there. Pilosha? There or not? Right. The last one. Object-based image analysis. You have image, you have pixels, you segregate the pixels into vectors or polygons, and you define classes on top. Now you see, you start with the image, right? And then you ended up with set of polygons. This is called objects. So each polygon is an object. So this is object-based image analysis, or we call this segmentation. So basically, you can divide the image into non-overlapping objects, right? There are different ways of doing this segmentation technique at image level, at object level, and pixel level. Top-down and bottom-up approaches are there. So you can see top-down approach. You take the image and you segregate it into objects at the pixel level with a scale of 10. Scale basically says the amount of details, right? Maybe the size of pixel can be considered as image detail, or maybe the ratio between a pixel of this image and the object that you want to define on this image, the ratio, right? So basically, also you can define objects on this image using chord tree approaches. You know what is chord tree? You divide each pixel into quad tree format and assign classes. And actually this quad tree segmentation is actually deteriorating the original image. But remember, I'm showing here a very, very nice picture image, but satellite images are not like this, okay? Multi-resolution segmentation, you can see all are polygons. And also multi-threshold segmentation, each area is thresholded by pixels and you can get different information. So basically, this is actually the segmentation process. You have a segment, you merge all the segments that belongs to this segment and you get the whole segment. Or otherwise, you just start with a small segment and grow the segment. So you can grow it till you get the object that you want. So this is a segmentation process. And this is different from the classification, but basically at the end what you get is a set of pixels or set of objects that are belong to a particular class. Okay, so I just try to wind up now. I talked about, you asked me to talk about satellite image processing. It's a wonderful area. It's an area that we should learn for a lifetime, as you have seen how much of information is there. Generally, I talked about 4 very important satellite image processing techniques: classification, change detection, diffusion, and segmentation. Object-based classification, pixel-based classification is classification, object-based classification is segmentation. And each area is a very deep area to study and to understand and to work on. So it requires a lot of time, requires a lot of patience, and requires a lot of time from your life in order to achieve understanding all in all these areas. But what I talked about is the commercial areas that are very, very famous in satellite image processing. When it comes to these NASA space apps, images can be used in these areas. You can do a classification on the images given by NASA. You can do a fusion on the images given by NASA according to your objective. You can work on a object-based classification on the data given to you to develop a particular application. So you'll be working on different areas in this large, diverse areas that I talked about. But you'll be working on them. In the end, you'll be working on either of these areas. Outside these areas, there are advanced image processing techniques. For instance, differential INSAR, interferometric SAR, digital elevation model generation, subpixel classification methods, atmospheric modeling on satellite images. Likewise, it is very diverse. What I'm showing here, as I said, is the central image. It is like 93 GB image of Sri Lanka. It's a mosaic from Sentinel-1 synthetic aperture radar image. This was a very nice image, though it shows it looks very bad. And this is the very recent express pearl oil spill from Sentinel-1. This is interferogram over Sri Lanka. This is deformation over Sri Lanka. This is digital elevation model of 𝐿, right? So there are diverse areas of satellite image processing that you have to engage in. The talk that I gave you today does not talk about these advanced processing mechanisms. So there's a lot to learn. And in order to learn all that, you have to understand mathematics, statistics, as well as in tandem computer programming and all. So where can we do these things? There are a lot many tools, as I have summarized here, in order to do them, right? Most of them you know. So these are leading commercial and open source environments that you can use in order to do what I said: classification, fusion, segmentation, change detection, mainly. And also, if you want to advance studies, you can use them. And these are the societies for remote sensing. ISPRS is the leading society for photogrammetry and remote sensing in the world. And I want to thank the DLR for the materials that was used in this presentation. And I want to thank you, SEDS, Sabra, especially for giving me this opportunity to talk about satellite image processing. It's a huge area, as I said, but I try to run across a very large cross-section so that you can get an idea and you can think before processing. So I think I will finish this now, and if there is any questions, I'll be happy to answer. Thank you for listening.
Thank you so much, Dr. Duminda, for your informative and productive session. So as we have promised you earlier, I hope our audience sure may got so many questions regarding this. So now, the participants, it's your chance. The floor is all yours to ask any questions using the chat box down below, or you can use the option of raising hand as well.
Well, if you guys are really tired, you can write to me, right, and ask questions also. I will give you that chance as well. Of course, you can ask anything right now, and if you want detailed understanding, please you can write to my email as well.
Hello, sir.
Yes.
I have a question that you said that when you take
Anupa, can you speak a little bit louder? I can't hear you.
Hello? Am I audible?
Yeah. Now.
I remember that you said that when we take in SAR images, we take those images with an angle.
Yeah.
So I think when we get like that, that image could be warped, and how can we go through that?
Yeah, very good question, Anupa. SAR is actually it's a slant range image. It's not ground. It's not. It's an oblique image. It's not nadir looking image, as I said. Just 1 minute. Okay. I will just get to this where I talk about this. So you can see in this what happened is actually the SAR image sends pulses on a slant range. And when it hits somewhere, it goes back. And the pulses hitting the target will be recorded in the image. Now, how it records? Along a slant plane. So what happened is that all the image that is recorded along this plane, because whatever that hit and came back came along this plane, right? But you know, if we know the angle here, that means the angle of the slant plane with respect to this plumb line, that is the look angle, what we call, and also the angle at the bottom here, that means the plumb line, and the slant range, that is called the local incidence angle. Then of course we can convert this slant plane by using cos theta to the ground range. So all the pixels that is recorded along the slant range will be converted to ground range. So basically the slant range image multiplied by cos theta, for instance, very simply I'm saying, okay, but it is more complex than this, right? Then we will get an image along the ground range. So we convert the slant range image to ground range, and that ground range image will be matched with the ground range image coming from the optical sensors. That is basically what is happening. All right? Anupa?
Okay, sir. I think I get that.
A little bit more you want to know?
Sure, sir. That will be better.
Just 1 minute, okay? Just. I did not prepare for, I need a figure. Fortunately, I don't have the drawing capabilities on, but that's why I should have taken that drawing capability, otherwise I would have gone. Wait, I will. Let me see. Maybe I have a document. Yeah. Now you can see the slant range. Can you see this, Anupa?
Yes, sir.
So basically, these are the original images. When we download images of SAR, it will be like this disturbing image. But we have to convert this into this sort of image. So basically, what we do is actually we convert the slant range. That means you can see this is actually the slant range. It is quite elongated along the line of sight, which we call the line of sight. This is the line of sight. This is the line of sight. Elongated along across that. So we have to convert that into projection. That the same image you can see converted into ground range. Previously, this is this way, but you know Putlam is on the other side. So we have to convert it into ground range and then convert it into the geo coordinates, that mean coordinations. Once you give it to proper geometric correction, then the Putlam comes to this side. Basically that, for now, Anupa, I will talk about this, I will send you detailed description with the drawing. I need to draw, but I don't have the capabilities to draw, and I have to find the presentation where that particular drawing is there. But to explain this, I need at least 3 drawings. Okay. For now, just the understanding, this look angle and the incidence angle is used to convert the slant range into ground range. And when you convert it into the ground range, what happened is that along the slant range, if there are 2 buildings, we cannot measure the distance. But if we convert it into ground range, of course, you know, from this building to the other building, how much is the distance? So whatever the distance or the spatial relationship between buildings can be taken only along the ground range, not on the slant range. That's why we have to convert the slant range into ground range. Of course, in that case, we use the cos theta, or maybe the theta is actually the incidence angle, the angle between the perpendicular at the ground and the line of sight. Now, remember, this is only for flat terrains, okay? I am showing here is a flat terrain, but remember when there is a mountain, this slant range is not this perpendicular to the surface, is not the perpendicular at the flat terrain. So things become more complex, right? So SAR image processing in high altitude areas and SAR image processing in flat terrains are completely different. So when the terrain is getting rougher, heterogeneous, and more undulated, SAR image processing becomes much more challenging. But you know, the theta angle, incidence angle, always shows us a way. to come out of that. Okay. Anup, I will explain to you once I get in touch with you for something else one day.
Okay.
And give me a call. I'll explain.
Thank you.
Thank you, Dimi, for the appreciation. Thank you. I hope you understand what I said and got some bits and pieces from that. Thank you.
So do we have any other questions from the audience?
I think they want to, most of the guys want to see the India-Sri Lanka match, I think.
Yes, exactly. So yes, so in case they got any questions, I think as you have told us, they can contact you through your email. So if better, you can put it in the chat box so they can copy and so on. So as we don't have any other questions for this one, I would like to give my gratitude and thank you for you, Dr. Duminda, for giving us a very valuable and informative session. And I hope our audience has gained so many things from this session. So we truly appreciate a person like you who is willing to give your talent and time in enriching the youth of ours. So yes, and for the participants, thank you so much for being a beautiful audience with us. And I'm inviting all of you to join with us in upcoming webinar series as well. And just get acknowledged yourself. So with the hope of that, with the hope of seeing all of you again, thank you everyone and have a good night.
Thank you very much. Thank you.
Thank you very much.
Okay, bye-bye and greetings and blessings from Japan. Okay, stay safe, everyone. And don't take any chances with the Delta wave. Okay? Bye. Okay, bye-bye.
Bye-bye.
Bye, sir. Good night.
Good night.